Hello everyone, and welcome back to the Fluctus channel. Propellers work by converting rotational motion into thrust, using twisted blades to push water backward and the ship or boat forward. Before propellers were invented in the early 1800s, ships were primarily moved by wind using sails or human rowers. The invention of the propeller changed all of this. Over the years, these devices have undergone many changes and improvements, from simple fixed-pitch propellers to ducted propellers to specialized thrusters and water jets. Yet, propellers are not perfect. Virtually all ship propellers are subject to often harsh environmental and operational factors that can lead to their degradation. These factors can affect a propeller's performance, efficiency, and lifespan. Factors that can affect propeller function include corrosion from salt and sea life exposure, the growth of barnacles and algae, and abrasion due to small particles, salt, and debris. To keep these propellers in working order, such issues must be addressed as soon as possible. Depending on the size of the propeller, removing it for repair can be a very difficult process. Some of the largest ship propellers are up to 30 feet in diameter and can weigh well over 100 tons. Even when placed in a dry dock, removing such massive propellers can take up to a dozen people and specialized equipment. In many cases, repairing a severely damaged propeller will involve adding material to the surface. This can be done by welding or using specialized metal deposition techniques and materials that closely match the propeller's original composition to ensure integrity and performance. After the propeller is machined to the correct shape, it must be balanced to ensure it operates smoothly and does not cause vibration in the ship's driveline. This is a critical step and requires precise adjustments and computerized input. The propeller is also polished to reduce drag and improve efficiency, restoring its hydrodynamic performance. Before polishing, the propeller is cleaned to remove marine growth, corrosion, and any other debris. High-pressure water jets, scraping tools, and chemical cleaners may be used. The actual polishing is done using special tools and abrasives. It can be performed underwater by divers or in a dry dock if the ship is undergoing maintenance. The polishing process involves several grades of abrasives to gradually smooth the propeller surface. The goal is to achieve a mirror-like finish, minimizing hydrodynamic resistance. For large ships, a properly polished propeller can save millions in operating costs over the boat's life. Due to their importance to performance, repaired propellers will be reinstalled and evaluated through sea trials before they are cleared for permanent operation. During this process, technicians will measure the speed of the ship at various engine power levels to evaluate the propeller's efficiency in converting engine power into thrust, perform vibration analysis, noise analysis, and more. These tests help identify any issues that need to be addressed before the ship enters service. Though many ship propellers follow a similar design, engineers continue to develop new shapes and styles in an effort to improve efficiency, increase thrust, or reduce wear. Thanks to computer-aided design, our concept of what a propeller can do continues to advance. Perhaps one of the biggest advancements in propeller technology is the azimuth thruster. Designed for advanced maneuverability, these unique propellers can rotate 360 degrees, giving ships the ability to change direction without changing the vessel's orientation. In contrast, traditional propellers are fixed in place and rely on a rudder to steer the ship. Manufacturing any propeller starts by creating a pattern of the propeller from wood, plastic, or metal, which is easier to shape than the final material. This pattern then creates a mold, often made from sand. Once the mold is cast, the material for the propeller is melted in a furnace and then poured into the mold cavity. After the material is poured, it is allowed to cool and solidify. At this point, the mold is broken and the propeller is machined, ground, and polished. Once all the parts of the azimuth thruster are manufactured, they are assembled into the final thruster unit. This involves mounting the propeller on the motor shaft, installing the motor and steering mechanism into the housing, and connecting all the electrical or hydraulic systems. The assembly process requires careful alignment and calibration to ensure the thruster operates efficiently and reliably, and can be particularly challenging due to the size of the parts involved. Once the completed azimuth thruster is installed on the vessel, rigorous testing must be performed to verify its performance and reliability. This can include dry testing of the motor and steering mechanism, as well as wet testing of the entire unit to simulate realistic operating conditions. Throughout its life, the thruster unit must be regularly cleaned and maintained, both in the water and on land. Inspections typically involve checking for any visible damage, wear, or corrosion on the propeller blades, seals, and thruster's housing. As with other propellers, they are often removed for detailed inspection, repair, or replacement. Issues like nicks, cracks, or erosion can be addressed through welding, machining, or polishing, often at regular intervals. One of the most innovative types of boat propulsion uses the water itself to generate thrust. This is known as water jet propulsion. It works by drawing water from beneath the boat and expelling it through a nozzle at the rear. The heart of a water jet propulsion system is its pump, usually a type of centrifugal pump powered by an impeller. In the simplest terms, the impeller draws water from the intake into the pump. As it spins, its blades push water outwards towards the centrifugal force, accelerating the water's pressure and speed. Steering, meanwhile, is achieved by redirecting the flow of water exiting the nozzle. As with azimuth thrusters, by turning the nozzle to the left or right, the operator can control the direction of the craft without needing rudders. As jet propulsion designs change and improve, they need to be properly tested, typically via sea trials. In this process, a vessel is put through various tests to evaluate the performance of the water jet propulsion system. This includes acceleration tests, top speed runs, and tests at different power settings to evaluate the system's efficiency. The vessel will also perform drastic maneuvers, such as sharp turns, figure eights, and reverse maneuvers, which help assess steering responsiveness and agility. In recent years, water jet systems have become a common fixture on large-scale catamarans, particularly luxury boats and ferries. Catamarans are multi-hulled watercraft with at least two parallel hulls of equal size. This design offers several advantages, most notably the superior stability that comes from reduced rolling and pitching. This makes catamarans more comfortable for passengers and crew, especially in rough seas. They can also move faster than monohulls of similar length, because their twin hulls produce less hydrodynamic drag. Jet propulsion systems are particularly well suited for catamaran-style boats because they enable shallow water operation, reduce drag, and tend to be more efficient at high speeds. One of the oldest methods of propelling a boat is to use wind propulsion. However, wind sailing has evolved quite a bit since the days of the tall ships. Though sails are often still used by smaller vessels, engineers have recently set their minds to developing new ways to harness this natural power to save time, energy, and money. A primary example of this is wind wings. These consist of large wing sails that can be retrofitted onto cargo ships, reducing reliance on traditional fossil fuels. Wind wings are expected to generate average fuel savings of up to 30%. Though they do not replace traditional engines, they do supplement them in a way that saves as much as 3 tons of fuel per day. Another wind-based innovation is the rotor sail. These consist of tall, cylindrical rotors mounted on the deck of a ship. When these rotors spin, they interact with the oncoming air, creating a pressure differential through a phenomenon known as the Magnus effect. This differential exerts a force on the rotor, propelling the ship forward. Like wind wings, rotor sails are intended to supplement a ship's engines to save money on fuel and improve efficiency. Finally, there are sky sails. This is basically a large kite for ships. Because it operates at altitudes where wind conditions are more favorable, it can help save large ships as much as 10 tons of oil per day. Such innovations further prove that sometimes the best technology is found in combining the old with the new. That's the end of this video. I hope you enjoyed it. Make sure to subscribe to this channel so you don't miss any of our new content. See you next time.